Have you ever wondered how the size, complexity, and quality of a software product are measured? Well, meeting such curiosity, we have product metrics. These handy tools in software development measure different attributes of a software product. They provide an insight into the product's size, its intricacy, and even its quality. Now, there are various types of product metrics, but today we'll focus on two key types: lines of code or LOC-Based metrics, and function points or FP-based metrics. These metrics are not just numbers. They are a mirror reflecting the heart and soul of the software. They help in making informed decisions, planning for the future, and ensuring the software's success. So they're pretty important, wouldn't you agree? In the next few minutes, we'll dive deeper into what these metrics are and how they work. So gear up for an insightful journey into the world of product metrics. First, let's talk about LOC, or lines of code-based metrics. These metrics are quite straightforward. They're all about counting lines in a software's source code. The first of these, total lines of code, or TLOC, is a basic measure of a software's size. It's simply the sum of all lines in the source code files. And yes, this includes comments and blank lines. Next, we have executable lines of code, or ELOC. This metric narrows down TLOC to only those lines that contribute to the software's functionality. So, unlike TLOC, ELOC excludes comments and blank lines, focusing only on what makes the software work. Then there's lines of code per function, or LCPF. This one gives us an average count of lines of code in each function or module. LCPF is a handy way to gauge code density and granularity. Think of it as a measure of how much code is packed into each function. Moving on, we have lines of code per requirement, or LCPR. This metric takes the average number of lines of code implemented for each software requirement. It's an excellent way to get a sense of how efficiently requirements are being implemented in the code. Lastly, we have lines of code change, or LOC change. This metric keeps track of the number of lines of code that have been added, modified, or deleted during software maintenance activities. It's quite useful for understanding how much the software evolves over time. Each of these metrics gives us a different perspective on the software's code. TLOC and ELOC help us understand its size. LCPF and LCPR give us insights into its structure and implementation efficiency. LOC change, on the other hand, reveals how the software changes and grows. While LOC-based metrics provide us with valuable insights, they do have some limitations, which we'll discuss next. LOC-based metrics, like any measurement tool, have their strengths and weaknesses. Starting with their strength, LOC-based metrics are remarkably easy to measure. With automated tools readily available, it's a breeze to count the number of lines in a software codebase. This ease of measurement is a significant advantage, especially when dealing with large-scale projects where manual counting could be a logistical nightmare. Another advantage of LOC-based metrics is that they provide a direct indication of the software size. By counting the lines of code, we can get an immediate sense of how large or small the codebase is. This makes LOC-based metrics a straightforward and intuitive measure of software size, which is widely understood and accepted in the industry. But just as a coin has two sides, LOC-based metrics have their limitations. One of the main drawbacks is that they do not account for differences in complexity or functionality between different lines of code. A single line of code can range from a simple variable declaration to a complex logical operation. Yet in LOC metrics, they both count as one line, which can lead to misleading results. Additionally, LOC-based metrics are susceptible to variations in coding style and conventions. Different programmers have different styles of writing code. Some prefer compact, dense code, while others opt for more spaced-out, verbose code. This variation can significantly influence the LOC count, making it an unreliable measure of effort or complexity. Finally, LOC-based metrics may not accurately reflect software size or effort required for non-code artifacts. Software development involves more than just coding. It includes designing user interfaces, creating databases, writing documentation, and more. Since LOC metrics only count lines of code, they may underestimate the size and effort of these non-code elements. Now, let's shift our focus to another type of product metric: function points. Function points, or FP-based metrics, provide a different perspective on measuring software. Rather than focusing on the physical lines of code, FP-based metrics consider the functional requirements and complexity of software, providing a more comprehensive measure of size and effort. The first metric we'll explore is total function points, or TFP. This is calculated based on the software's functional requirements, complexity, and user interactions. TFP gives a snapshot of the overall size of the software from a functionality perspective. Next up is function points per unit of time, often abbreviated as FPUT. This metric indicates the average rate at which function points are developed or delivered over a specified time period. It's a measure of productivity, showing how quickly the development team can turn functional requirements into working software. Function points per person month, or FPPM, takes this concept a step further. This metric normalizes productivity by team size and duration, providing a better comparison across different teams and projects. It essentially tells us how many function points are developed per person month of effort. Function points per function, or FPF, gives insight into implementation efficiency. This metric shows the average number of function points implemented per functional requirement or module. It's a great indicator of how effectively the team is translating requirements into functional software. Finally, we have defects per function point, abbreviated as DPFP. This metric shows the number of defects or errors identified per function point. It's a measure of software quality and reliability relative to its size. A lower DPFP indicates a higher quality software product. In a nutshell, FP-based metrics provide a holistic view of software size, productivity, efficiency, and quality. They offer valuable insights that can help in estimating effort, cost, and schedule more accurately, benchmarking performance, and improving processes. Similar to LOC metrics, FP-based metrics also come with their own set of advantages and limitations. FP-based metrics offer a more holistic measure of software size, but they aren't perfect. Let's delve into the advantages and disadvantages of these metrics. Firstly, the beauty of FP-based metrics lies in their ability to consider the functional requirements and the complexity of the software. Unlike LOC metrics that merely count lines, FP-based metrics take into account the functionality and user interactions of the software. This provides a more comprehensive picture of the software's size, which in turn helps in estimating the effort, cost, and schedule more accurately. Another significant advantage of FP-based metrics is their ability to facilitate benchmarking and comparison across projects and organizations. This is particularly useful when you need to compare the productivity or quality of different teams, or analyze the efficiency of different methods or tools. However, as with anything, FP-based metrics do come with their own set of limitations. For instance, they require a detailed understanding of the software's functional requirements and complexity factors. This means that it's not as simple as just counting lines of code. You need to understand what the software does, how it does it, and the level of complexity involved. This can be quite a challenge, especially for larger or more complex software systems. Additionally, the process of manually counting function points can be quite time-consuming and subjective. Different people might count function points differently, leading to inconsistencies and potential disputes. And while there are automated tools for function point counting, they may not always be accurate, especially for complex or unconventional software designs. Lastly, FP-based metrics may be less precise for projects with significant non-functional requirements or architectural complexity. This is because they primarily focus on functional requirements and user interactions, potentially overlooking other important aspects of the software. As we've seen, both LOC and FP-based metrics have their own strengths and weaknesses. It's all about understanding these metrics, their advantages and limitations, and knowing when to use which. We've covered a lot of ground today, so let's quickly recap. We delved into the world of product metrics in software engineering, primarily focusing on lines of code, or LOC-based metrics, and function points, or FP-based metrics. We discussed how LOC metrics, while easy to measure and widely accepted, can potentially overlook differences in complexity or functionality, and may not accurately reflect the effort required for non-code artifacts. On the other hand, FP metrics, which consider functional requirements and complexity, can help estimate effort, cost, and schedule more accurately. However, they require a detailed understanding of the software's functional requirements and can be time-consuming to count manually. It's important to remember that every metric has its strengths and weaknesses, and the choice between LOC and FP metrics or any other type of metric should be based on your specific project needs. Remember, the right metric depends on the specific context and goals of your software project. Happy coding!